Good morning and welcome back to Heat Transfer. Today we're going to finish up the problem that I was working the last time, which was for flow over a cylinder, which is external flow covered in Chapter 7. And we'll get into the topics from Chapter 8, which is internal flow. So still convection, but for consideration where the fluid is confined to a flow path like a tube or a duct, and consider how we calculate heat transfer coefficients that allow us to consider heat transfer between the solid surface on the inside of a tube that has a gas or liquid flowing through it, or just generally a fluid. So I'm going to start sharing my screen now so that we can get back to the problem that we were looking at the last time. All right, here we go. So again, from this was was called external flow. So fluid flow over a cylinder, over a flat plate, could be over a square shape, etc. But we consider how we would write expressions that allow us to calculate the heat transfer coefficient to then calculate heat fluxes by convection or heat transfer rates by convection. So we looked, I'll go back a couple here and consider, just for review, for flow over a flat plate. Let's see here. We had some expressions for boundary layer thickness, whether that be the laminar boundary layer or the turbulent boundary layer. We had an expression that we could write to determine the thickness of that layer as a function of position, as we measure from the leading edge of the plate to the trailing edge, such that the rate at which the boundary layer will grow, where, let's say here, the velocity boundary layer will grow as a function of position when it's a laminar flow, and then once it transitions to a turbulent flow, there are different expressions, so that the velocity boundary layer is that place where the velocity varies between the free stream velocity, which is a constant value outside the velocity boundary layer, and it's a zero due to the no-slip condition at the surface of the plate. Now, to get to heat transfer calculations, we considered the expression of Nusselt number correlations, where we would use the definition of the Nusselt number. So the local Nusselt number here, NU sub x, is just defined as the local heat transfer coefficient H sub x times the x position divided by the thermal conductivity of the fluid. So if we define an expression for the Nusselt number, then we can define an expression for the local heat transfer coefficient, so that in the laminar region, we could calculate the heat transfer coefficient as a function of position. And also, as it gets to the turbulent condition, we use the same definition of the Nusselt number, but equate it to a different correlation for how the heat transfer coefficient varies as a function of x, so that we could then write expressions that describe what I have here in red as the heat transfer coefficient as a function of position in the laminar region and the turbulent region, so that we can then calculate heat fluxes, in that this local heat transfer coefficient times the temperature difference that exists between the surface and the fluid can then, that expression can be used to find the local heat flux based on the local heat transfer coefficient. Now, all the properties that are used to write the expressions for the Reynolds number and the Nusselt number when dealing with flow over a flat plate are based on this film temperature that is T sub F. It's just the surface temperature plus the free stream temperature of the fluid divided by 2. And that expression is considered because inside the thermal boundary layer that grows over the plate, the temperature is somewhere between the surface temperature and the ambient temperature, so that this evaluation is just an average temperature for all the fluid molecules that would exist inside of that film. So we went through the last time and considered how we would calculate the heat flux at L over 2 at the halfway down the length of the plate, and also at the length of the plate. So we use those expressions for flow over a flat plate. Oh, and actually, yeah, to calculate the heat fluxes at those positions, and then the average heat transfer, the average heat flux. Such that the average heat flux is just based on the consideration that the heat transfer coefficient varies along the entire length of the plate. The local heat flux is just the flux at those particular positions. So in this problem, we found that, excuse me, we found that the Reynolds number at the trailing edge of the plate is less than 500 thousandths, which is the transition point for the flow from laminar to turbulent. So if it's a laminar at the trailing edge of the plate, it's going to be laminar over the entire length of the plate. So when we calculated the heat transfer coefficient, or the Nusselt number at x equals L, and then the heat transfer coefficient at x equals L, we could calculate then the heat flux as just that local heat transfer coefficient at x equals L times the temperature difference to give us the heat flux. And now these are negative because in this problem, I indicated that the fluid temperature was higher than the surface temperature here. At x equals L over 2, we evaluated the Nusselt number and also the heat transfer coefficient so that we could then write the expression for the heat flux at L over 2, so that the expression of the heat flux can be calculated. And it too is negative just because, again, the temperature difference between the surface and the fluid ends up being a negative quantity, which just says the heat transfer rate is into the into the plate from the fluid, since the fluid's at a higher temperature. The expression of the average heat transfer coefficient to get the average heat flux is based on the Nusselt number correlation for for laminar flow over the plate. And so we calculated the average value and then get the average heat flux. So the local heat fluxes are just based on the local heat transfer coefficient, and average heat flux is going to be based on the average heat transfer coefficient that exists over the entire plate. So we also considered a problem where at the trailing edge of the plate, it was a turbulent flow. So if it's a turbulent flow, it just says that at the trailing edge of the plate, it says that there's a laminar region and a turbulent region. And we determined by calculation of the transition point, which is where we just set the Reynolds number, or set the Reynolds number here equal to 5 times 10 to the 5th, which is equal to the free stream velocity times the critical, or this is a transition point, which is used to calculate what is called the critical Reynolds number. But along with the transition point is the place at which we have a transition from laminar to turbulent flow. And so that will be what's called a critical Reynolds number, which is a particular point where the Reynolds number is equal to 5 times 10 to the 5th. So we've found that position along this plate that was 0.5 meters long, that the transition would occur at 23 centimeters here. So it just says that the laminar region extends from x equals 0 to 23 centimeters. And then the turbulent region from that same position to the trailing edge at 50 centimeters. So that says that I would have an average heat transfer coefficient that exists in the laminar region, an average heat transfer coefficient that exists in the turbulent region, and the expression of the average heat transfer coefficient over the plate would be essentially an expression of a weighted average according to the length of the laminar region and the turbulent region. But we have a single correlation that we can use when we know that there's a laminar and a turbulent region, and that is the one that we referred to here, which is a Nusselt number is 0.037 Reynolds to the 4/5 minus 871, that quantity multiplied by the Prandtl number to the 1/3 power, so that the average heat transfer coefficient over the plate that had a laminar and turbulent region were taken into account, and the heat flux, that average heat flux over the entire plate, would just be that average heat transfer coefficient times the temperature difference between the fluid and the plate. And so we even went along and considered the average heat flux in just the laminar region, where we just considered that the laminar region ends at the point where we have the transition from laminar to turbulent. And so we can use that position of, it was 23.06 centimeters, and calculate based on the Nusselt number correlation for the average heat transfer coefficient over a laminar region. So for this Reynolds number, which is where that transition point occurs, the Reynolds number will be set to 5 times 10 to the 5th, using the same Prandtl number evaluated at the film property or at the film temperature. We get the Nusselt number. We can then calculate the average heat transfer coefficient here, which is 54.5526. And if we multiply by the temperature difference between the surface and the fluid, then we can get the average heat flux in the laminar region. So, so here it can, on this plot, an expression of the average heat transfer coefficient in the laminar region here, and drawn in this orange line here, and the average heat transfer coefficient that was calculated over the entire plate, which is 89.47. And just here just says that the average heat transfer coefficient in the turbulent section will be higher than this average value, taking into account that there's an average value for the laminar region that is lower than the 89.47. So I drew a qualitative expression of the heat transfer coefficient variation in the laminar region and in the turbulent region that would support these two calculated values for the average heat transfer coefficient in the laminar region and the average over the entire length of the plate. And so we considered also that external flow applies not only to the flat plate, but also to cylinders and spheres that have fluid flowing over them. But due to the way that the fluid interacts with those surfaces as it moves over the surface, we have different expressions of the correlations that are used to define the Nusselt number. Here, the Nusselt number is still defined as a heat transfer coefficient times a characteristic length over the thermal conductivity. But here, that characteristic length is just the diameter of either the cylinder or the sphere. And so there's only one value for the Nusselt number. It doesn't change as a function of position like it does for flow over a flat plate. And so there's a single correlation that would be that I presented the last time for the expression of a Nusselt number for flow over a cylinder, where the Reynolds number and the Prandtl number are still used to define the Nusselt number. It's just the construction of the correlation based on empirical investigations just give us a final form of that expression for the Nusselt number, still in terms of the Reynolds number and Prandtl number, but it just has different coefficients and powers associated with the quantities on the Reynolds and the Prandtl numbers to represent what's actually happening over these surfaces here for a cylinder. The Reynolds number is also a single value like the Nusselt number for flow over a cylinder and also for flow over a sphere, and that is the free stream velocity times the diameter divided by the kinematic viscosity. So once we've evaluated the Reynolds number and we use it, it doesn't change as a function of position. So the way that we get a heat transfer coefficient, which would be an average heat transfer coefficient, is just to rearrange a definition of the Nusselt number for H, which just says K over D times the Nusselt number, will give us the heat transfer coefficient such that the Nusselt number correlation that is appropriate for that flow condition would give us the value for the heat transfer coefficient once it's selected. And once we have the heat transfer coefficient, it's just multiplied by the temperature difference between the object and the fluid to then get the heat flux. And of course, the heat flux can be translated to a heat transfer rate once we multiply the heat flux by the surface area that's actually experiencing that heat transfer by convection. So the heat flux, again, times the surface area is a heat transfer rate. Now, for this particular correlation, all the properties are evaluated at the film temperature. So when calculating the Prandtl number or looking it up and calculating the Reynolds number, where we have to look up the kinematic viscosity, those properties are all evaluated at the free stream temperature. So that it's just, the film temperature, which is the average of the surface temperature and the free stream temperature, T infinity. Now, when we're dealing with a sphere, this expression for the Nusselt number involves, again, the Reynolds number, the Prandtl number, but also specifically the dynamic viscosity evaluated at the free stream temperature and the dynamic viscosity evaluated at the surface temperature. For this correlation for flow over a sphere, the properties are not evaluated at the film temperature. All the properties are evaluated at the free stream temperature, except for mu sub s, which is evaluated at the surface temperature. So when using this expression to calculate heat transfer to or from a sphere, where there's a fluid flowing over it, whether it be water, oil, glycerin, air, helium, whatever fluid is flowing over it, that fluid's properties are captured in the Reynolds number and the Prandtl number, along with these dynamic viscosities. But the properties are all going to be evaluated at the free stream temperature and the surface temperature for this particular correlation. Now, in table 7.1, which is what I referred to before we started the last problem, is an expression of Nusselt number correlations for multiple shapes. And actually, I'm going to reference that. I put this here in the figures. Right here. So if we're using this table, which is a result of multiple investigations into flow over a cylinder, or what we call non-circular cylinders, in that we have these different shapes. The fluid is flowing here from left to right, or it could be right to left, but it's just flowing over the perimeter of each of these circular and non-circular cylinders. But depending on the Reynolds number that you calculate, there's a slightly different Nusselt number for each one of these geometries. Now, the expression that I gave you before for flow over a cylinder, it doesn't matter there's no range of Reynolds numbers for a different value of a different correlation. There's a much larger Nusselt number, or much larger range of Reynolds numbers for which that particular correlation is applicable. And actually, it's like, let me go back to it really quickly here. Here, when dealing with this expression to calculate the Nusselt number and then get a heat transfer coefficient, the only requirement for the use of this particular equation is that here the Reynolds number times the Prandtl number must be greater than 0.2 in order to use this expression. Now, this meets a lot of conditions. For air, the Prandtl number is 0.7 something. So at typical temperatures for atmospheric pressure, if the Prandtl number is 0.7, that means a Reynolds number of 1 still meets this requirement, which would be a extremely laminar flow. If the Reynolds number is a greater value times the same Prandtl number is still going to be greater than 0.2. This expression applies to just about any flow configuration that you might find in a typical engineering application. So it's been verified and considered for all kinds of external flows over a circular cylinder. This is only applicable to a circular cylinder. But particularly when you venture off into other cylinders, non-circular cylinders, is when we refer to this expression. So that here, if you're dealing with a circular cylinder, And using this table, you'd have to select according to your Reynolds number. If your Reynolds number is 100, then you would select a Nusselt number correlation that is this one here. If the Reynolds number is 10,000, it would be a slightly different expression, which has different exponents on the Reynolds number and a different coefficient multiplied by the Reynolds number. But this is typically for this, when this table is referenced, it's not for a circular cylinder, because we usually use the previous expression for the calculation of a Nusselt number to get a heat transfer coefficient. This table is particularly useful when we have these non-circular cylinders to consider expressions for, because for these, the same type of correlation as I referenced on the previous page is not really a given. So this expression, or these expressions for Nusselt numbers, eventually allow us to get to heat transfer coefficients, because the Nusselt number is just defined as H times the characteristic length divided by K, where the characteristic length for these non-circular cylinders, or for a cylinder, just would be the diameter. Now, here, these D's that are specified are just the expressions, since these are not actually diameters. If this is a square, the diameter used to calculate the Reynolds number, recall that the Reynolds number for a cylinder is still going to be the free stream velocity times the diameter divided by the kinematic viscosity. So if you're having to evaluate and look for an average heat transfer coefficient over any of these shapes, this diameter that is used to calculate the Reynolds number would be the length. Here, this would just be the length of a side of the square. This is a square tilted by 45 degrees. The diameter is actually this diagonal, or which would be the hypotenuse for a triangle that bisects this diamond shape. And if for the hexagon shape, where here it's on a flat side, or sitting on a flat side, or here sitting on a point. So this is how these D's here are expressions of the diameters that are that will be used in the Reynolds number. That is a part of the Nusselt number correlation for those that are referenced from this particular table. So the last time I specified a problem statement here, we considered a cylinder in a cross flow. Here, this would be a circular cylinder with a given diameter, surface temperature, and an air temperature flowing over it. And here we're going to consider, well, what is the heat flux from the surface? And we're going to use the correlation that it's valid for the Reynolds number times Prandtl number raised to the 0.2. So this correlation, and the appropriate correlation from table 7-1, because they're different correlations, you will get different values calculated for the Nusselt number, and thus different values for the heat transfer coefficients. So in practice, when using a particular correlation, this is the reason that references to the correlations that are selected for a particular problem are important, so that someone who is evaluating the work knows what assumptions were made, and what conditions were present for the calculation of a given quantity. Here, for calculating a given heat flux, with the surface temperature and the fluid temperature being provided, the method for determination of the heat transfer coefficient is what has to be considered based on the quantities that are actually calculated, and along the way to getting to what this heat flux is. So we considered that the Reynolds number is something that we would definitely need to calculate eventually to get to the heat flux, as the heat flux is just going to be the heat transfer coefficient times the temperature difference between the surface and the fluid. So for the consideration of the properties that we need evaluated at the film temperature of 50 degrees, we use table A15 to get these properties of atmospheric air at that given temperature. So here, the Reynolds number then is the free stream velocity. Here is 65, and this is, if I multiply here by, there's 3,600 seconds for an hour to get, and there are 1,000 meters per kilometer, so that we can get this expression in meters per second. And here, all right, so this is 18.0556 meters per second is the velocity here. So the the Reynolds number with the free stream velocity in meters per second here, 18.00055 meters per second, times the diameter, here's 12 centimeters, so 0.12 meters, divided by the kinematic viscosity, which is 1.798 times 10 to the minus 5 meters squared per second. So we have consistency of the units. So here times 0.12. All right, so I get a Reynolds number here of 120,504. So that Reynolds number is what we would use in the expressions of the for the flow over the cylinder. And the Reynolds, this is that Reynolds number that will be substituted into the expression that we considered for the definition of the Nusselt number for flow over a cylinder. So here, this Nusselt number, which I'm going to write first defined as H times D over K, is equal to 0.3 plus 0.62 times the Reynolds number to the 1/2, Prandtl to the 1/3. This quantity divided by 1 plus 0.4 over the Prandtl number. This quantity raised to the 2/3 this entire quantity in the denominator raised to the 1/4 times 1 plus the Reynolds number divided by 282,000 raised to the 5/8. This quantity raised to the 1/4. So we have the Reynolds number, we have the Prandtl number, so we can substitute those expressions into this expression to find the Nusselt number. We have the thermal conductivity and the diameter, so that we can then calculate the heat transfer coefficient that will be multiplied by the temperature difference here. So here, this Nusselt number, I have to plug a lot here into this calculator, plus 0.62 times the Reynolds number of 120,504 raised to the 1/2. The Prandtl number of 0.7228 to the 1/3. Here, 1 plus 0.4 over 0.7228 to the 2/3. This entire quantity to the 1/4. Times 1 plus the Reynolds number again of 120,504 over 282,000 to the 5/8 to the 1/4. And so this is how we'll come up with the Nusselt number for this expression. So 0.3. All right, should get enough brackets here. So 1/3. 1/4 of the punch. Let's see, I'll take a look again. Oh, yeah, it should be 4/5 there. Let's see here. Yeah, it should be 4/5, not 1/4. There you go. All right, and let's see this quantity divided by here. This is the 2/3. Sorry, make sure I got this entered correctly here. All right. .62. 2004. And let's divide it here by 1 plus 0.4, 0.7228 raised to the 2/3. Okay, make sure this is entered correctly here. All right, that's say this in a bracket here. Let's see here. All right, and the last one here, just making sure I get all of these entered correctly. 1 plus 120, 504. All right, and that one needs to be modified here. I think it's all at 0.62 there. All right, so here I've got a Nusselt number of 246.105. Looks like, yeah, that's correct there. So once the Nusselt number is determined, now we can write the expression for the heat transfer coefficient, which would be the thermal conductivity divided by the diameter times the Nusselt number. So the thermal conductivity here is 0.07235. The diameter is 0.12 meters, and the Nusselt number 246.105. So we can get the heat transfer coefficient over this surface. So here times 0.07235. And so here's 148.381 watts per square meter Kelvin. So that's our heat transfer coefficient based on the correlation for a flow over a cylinder, a circular cylinder, for any value of those times Prandtl number greater than 0.2. So this heat flux from the surface then is 148.381, according to this expression, times Ts minus T infinity, where the surface temperature was 90 degrees and the fluid temperature is 10 degrees. All right, so the heat flux then is 11,870.4 watts per square meter. So that heat flux that would be calculated for what's leaving this surface, if I have a surface area on the outside of the pipe, which will require the designation of a length, then this heat flux, so a heat transfer rate would just be the heat flux from the surface times whatever the surface area is. So if a length for the pipe or a length for the cylinder was defined, then this surface area would just be the perimeter pi d times the length of the pipe, and that would allow you to calculate a heat transfer rate for the problem once you have the heat flux. Now, selecting a different correlation, here we have a Reynolds number of 120,504. So if I go back to table 7.1, for our heat transfer, or our Reynolds number of 120,000, it falls in this range of 40,000 to 400,000, and it says that the Nusselt number correlation that we would use would be this one, and we would then use the same definition for the Nusselt number to get the value for the heat transfer coefficient. Yes, Aaron, this D that is defined for that particular shape, any places you would have a diameter used for those expressions would be the appropriate value. So when defining here, the characteristic length is the diameter. That's the D here. So for this expression for the range of Reynolds numbers, where ours falls in at about 120,000 for the Reynolds number, our Nusselt number here is 0.27 Reynolds to the 0.805, Prandtl to the 1/3. So here, the Reynolds number for RE is equal to 120,504, which falls between that 40,000 and 400,000. The Nusselt number was 0.027 times the Reynolds number raised to the 0.805 times the Prandtl number raised to the 1/3. This is again from table 7-1. So here, the Nusselt number is 0.027 times 120,504 to the 0.805 times the Prandtl number to the, and the Prandtl number here was 0.728 raised to the 1/3. So here, times all right, so here the Nusselt number is 298.247 for the for this correlation. So there's a difference here. A higher heat transfer coefficient will be calculated based on the Nusselt number is defined the same way, in that the heat transfer coefficient is still K over D times the Nusselt number. So the thermal conductivity is still 0.07235. The diameter is still 0.12 meters. So here, this right here. Times 0.07235. So here the heat transfer coefficient is 179.818 watts per meter squared Kelvin. So get a higher value for the heat transfer coefficient, and that's a slightly higher value for the heat flux. So here 14,385.4 as the heat flux. So at the end of so with these different values being calculated, it's important that the work that is shown in making that calculation indicates exactly what correlation is being used to write the expression for the Nusselt number, because from that Nusselt number is where we get the heat transfer coefficient necessary to calculate a heat flux for this problem. So the expression of the correlation is always going to give you a different value, but it's important that the requirements for the use of that particular correlation be satisfied. And here you can see, when we go back to the table, all of these expressions for the Nusselt number are based on Reynolds number and Prandtl number. But here in the leftmost column is the consideration first of, well, what is the configuration? Because the way that the fluid moves around each one of these cylinders is different, and thus it gives you a different heat transfer coefficient that you would expect due to the way that the fluid interacts with the surface as it moves around. And then according to the range of the Reynolds number, when that fluid is moving around that cylinder, we get a more specific expression of the Nusselt number based on how the fluid moves. The bottom section is just using a different equation. John, I'm not sure what you are referring to when you say the bottom section is just using a different equate that. Yeah, I don't know what that means there, or what you're trying to ask. So when referring to these expressions for the Nusselt number, it's in consideration of what the flow is like, where you solve for a heat flux a second time. So going back to your question, John, yes, that was at the beginning of the problem. I said I was going to solve it two ways by referring to two different correlations that I wrote out on the page as we solved the problem. These are two methods that they use the same Reynolds number. I used this Nusselt number correlation first, and I used this one and referred to it for our calculations here. Both methods are correct. As I was just going through and saying that it's just a matter of making sure that you refer to the correlation that is used to get the value for the Nusselt number, from which you take the value for the heat transfer coefficient for that particular problem. So whenever working the problem, you have Nusselt numbers that are Ricardo, the reason that I am referring to these different correlations is that, yes, they give different heat transfer coefficients. And at the very beginning of, or during the lecture last time, I communicated that different experiments are used with real fluids that have their own properties to develop these expressions. The expressions that are developed are presented using dimensionless parameters, Reynolds number and the Prandtl number for the Nusselt numbers, so that these expressions are fits of experimental data that is collected. So a correlation will give you a different value So the two correlations, though they apply to the same problems or to the same conditions, are not going to give you the same values. So both of them are correct if you specify which correlation is actually being used. So that's so when you're presenting results, if you're going through an analysis, the assumptions that are made, the expressions that are referenced are required so that someone who goes back and maybe wants to modify the work can follow that work and consider what things were considered when the calculation was being made. Both answers are correct. All right, so when considering a flow for the calculation of a heat transfer coefficient, Ricardo, both are correct as long as the correlation is specified for the calculation of the heat transfer coefficient. Now, if I tell you to use a specific one and you use a different one, then that would be incorrect. If I say use the correlation that requires that the Reynolds times the Prandtl number is greater than 0.2, then I'm being very specific in asking you to use that one. And so if you use a table when I ask to use a particular correlation, that would be incorrect. But if I say calculate the heat transfer or the heat flux from the problem that I just did, and I just told you that, then you have a choice as to which one you use. It's just a matter of making sure that you specify which one that you're actually using. So if you use that's Reynolds times Prandtl is greater than 0.2, that's appropriate if I did not specify the correlation. But if I do specify the correlation and use a different one than that, then at that point it would be considered incorrect. So here, whenever you're selecting a correlation, again, that is to eventually get a value for a heat transfer coefficient. Whether it's a Nusselt number calculation here for a cylinder or a sphere, which involves a Reynolds and Prandtl number, or for flow over a flat plate. The Nusselt number is a function of the Reynolds and Prandtl number, just the construction of the expression that is used to calculate that Nusselt number is different according to the flow geometry that is associated with that particular condition. If it's flow over flat plate and laminar or turbulent, you get a different expression for the Nusselt number. If it's flow over a cylinder or a sphere, you get a different expression. So all of those expressions can be used to find heat transfer coefficients. It's a matter of just selecting the appropriate one along as a part of your solution process to get to a value of the heat transfer coefficient. Again, all of the previous chapters where we considered convection occurring, the heat transfer coefficient was a given value, but now what we're seeking to do is to consider, based on the geometry of the problem, the fluids that are used, and the velocities of those fluids, what is the heat transfer coefficient that we should expect based on those parameters being specified in a problem statement. So for external flow, those are the correlations that that we cover for those kinds of those geometries. In Chapter 7, there's also flows across two banks, which is basically multiple cylinders in a cross flow, but now they're the wake of the fluid moving over a cylinder. So if I'm considering, let's say, a cylinder and there are multiple cylinders, well, if all of the streamlines were uniform before it got to this first cylinder, if I have another cylinder behind it and another cylinder behind it, the way that the fluid interacts with each one of those cylinders that are in line with one another changes, in that the conditions for the flow over each bank of cylinders is different. I don't cover that in class, but that is part of the coverage of Chapter 7, but it allows for the consideration of an average heat transfer coefficient that might exist for a what would be considered a bank of tubes, excuse me, which is the type of consideration or configuration that you would find in something like a heat exchanger or something like a radiator, such that the average heat transfer coefficient for all the tubes is what we'd be very interested in for heat transfer calculations in let's say if it's a radiator. But now, in consideration of something like a radiator or a heat exchanger, we have fluid flow. When we think about a radiator, we have fluid that flows on the inside and on the outside of the tubes. If you consider, let's say, the radiator in your vehicle, which is just a heat exchanger, it allows for heat transfer to occur between the engine coolant and the surrounding air as the air moves through the heat exchanger. So if you imagine, I'm looking down the end of a heat exchanger, and here these are the cross sections of the tubes. Well, actually, I'll draw it a little different way. So here I might have coolant or engine coolant here running through the tubes, and air flows over those tubes, so that there will be an external flow problem where air is moving over the outside of the tube, and an internal flow problem as the coolant moves through the tubes themselves. So in chapter 8 is a coverage of what is called internal force convection. We're pushing the fluid through a confined space here, which would be a duct, a pipe, a tube, and the heat transfer that occurs between that fluid and the inside of the pipe is our internal convection problem. And if you have airflow or some fluid flowing on the outside, that would be an external flow problem. So here is where we would have this. Of course, there'd have to be a balancing of the heat transfer. If I look here at the inside or a cross section of one of these tubes. So let's say on the inside, again, I have engine coolant, and I have air on the outside. Here we could construct what would look like a thermal circuit, in that I would have heat transfer from the engine coolant to the inner surface of the pipe. I would have heat transfer by conduction from the inner surface to the outer surface of the pipe. And I have heat transfer by convection from the outer surface of the pipe to the surrounding air. So if I wanted to draw a circuit here, a thermal circuit, which is from chapter 3, here this would be the temperature of the coolant, and here this would be the temperature of the air, so that there will be a thermal resistance due to convection, a thermal resistance due to conduction, and a thermal resistance due to convection on the outside of the pipe, such that here this would be the surface temperature on the inside of the pipe, and this would be the surface temperature on the outside of the pipe. In these definitions for the convection is where we'd have the heat transfer coefficient, in that the convection here would be 1 over H sub I times the surface area on the inside, where H sub I is indication of the heat transfer coefficient on the inside of the pipe. The heat transfer coefficient on the outside, H sub O times the surface area here, where this H sub O would come from a consideration of the flow of air over a circular cylinder. So we get an average heat transfer coefficient on the outside, and that will be my H sub O. In chapter 8, we'll go through, well, how do I get an average heat transfer coefficient for fluid that is actually flowing through the pipe? And of course, here for the resistance due to conduction here, this would be the natural log of the outer radius over the inner radius divided by 2 pi times K times L here for the conduction resistance. So in chapter 8, we're looking at, well, if a fluid is moving through a pipe, how do I find the heat transfer coefficient that exists along the length of, of that pipe so that I can come up with an average value? Now, when we're considering flow through a pipe, or what we call internal flows, again, we still have to consider the hydrodynamic problem and its effect on the thermal problem. We can't ever solve the hydrodynamic, can't ever solve the thermal problem without consideration of the hydrodynamic problem, because the hydrodynamic problem describes how the fluid interacts with the surface on the inside of the pipe. It affects what is happening in the thermal problem, where we actually have heat transfer occurring. So I'm going to actually refer to some of the figures that are presented in chapter 8 so that I don't have to just redraw them, but we'll talk about some of the physical problems associated with the internal flow problem, but we can't ignore what's going on hydrodynamically. Now, what am I referring to when I say the hydrodynamic problem? Well, that refers to, is it laminar or turbulent? When we consider laminar or turbulent for internal flows, Reynolds numbers less than 2300 are considered to be a laminar flow. Reynolds numbers greater than 10,000 are what we consider to be, well, technically we would call it fully turbulent. For Reynolds numbers that fall between 2300 and 10,000, we still label them as turbulent to make sure that they're not considered as laminar, but they wouldn't be considered fully turbulent. But often, anytime that the Reynolds number is greater than 2300, we would use the fully turbulent correlations. And the reason for that is that depending on the fluid that's actually used, when we're falling in this range between 2300 and 10,000 for the Reynolds number, the way that depending on the type of fluid that it is, the way that the heat transfer coefficients, or particularly the Nusselt numbers, would be calculated are very different. And so we just would consider that for Reynolds numbers greater than 2300, we just say it's not laminar. So it's just inappropriate to consider a laminar correlation anytime the Reynolds number is greater than 2300. But we would also consider that if we're going to select turbulent correlations, that we understand that the Reynolds number is greater than 10,000 for it to be fully turbulent, and for many of these correlations to be to have the type of accuracy that we would be looking for. But now this turbulent, again, is based on the Reynolds number, and that Reynolds number is going to be the average velocity of the fluid times the diameter divided by the kinematic viscosity. Now here, notice that this velocity is not a free stream velocity anymore. And that's because there is no free stream associated with a fluid that is moving through a pipe due to the no-slip condition. So if I have fluid moving through a pipe here, if we draw the velocity profile, let's say once it's fully developed here, let me draw this. Due to the no-slip condition, the velocity would be 0 at the radius of the pipe. So here, R and X. For the coordinate system, X is along the length of the pipe, and R is just through the radius of the pipe, here with the with the radius specified here is just capital R. Said R equals capital R, due to the no-slip condition, the velocity of the fluid would be 0, and along the center line, the velocity would be maximum. So the average velocity of the fluid that is referred to in the Reynolds number is the average velocity of the fluid that's moving through the pipe. Again, not an expression of a free stream velocity. The Reynolds number less than 2,300. Oh, yeah, I drew these incorrectly. Yeah, this is for Reynolds number less than 2,300. I wrote it incorrectly there. The value is considered to be a laminar flow. Less than 2,300 and greater than 10,000 for fully turbulent. So this is then for the Reynolds number for internal flows is based on an average velocity of the fluid, not the free stream velocity of the fluid, just because there is no actual free stream that exists. Now, this expression of the average velocity is the appropriate one to use, but often for internal flows, the mass flow rate of the fluid is what is typically going to be specified rather than the average velocity, let's say, of this engine coolant. The mass flow rate will be specified. But the relationship between mass flow rate and average velocity is just that the density times the cross-sectional area of the pipe times average velocity is the expression of a mass flow rate. So if the mass flow rate is specified, then this just says that the average velocity will be equal to the mass flow rate divided by the density times the cross-sectional area. So if we use this definition to substitute back into the expression for the Reynolds number, this says then that the Reynolds number would be equal to the mass flow rate times the density times, or divided by the density times the cross-sectional area times the diameter divided by the kinematic viscosity. Now recall that the kinematic viscosity is just the dynamic viscosity divided by the density. And the cross-sectional area, let's say for a circular pipe, is just pi d squared over 4. So here, with the kinematic viscosity is dynamic viscosity divided by the density, and the cross-sectional area, if it's a circular pipe, will be pi d squared divided by 4. So if I make those substitutions into this expression, here I get the mass flow rate over the density. With the cross-sectional area defined, this becomes pi d squared with a 4 in the numerator times the diameter, and with the kinematic viscosity defined as the dynamic viscosity divided by the density, this becomes mu in rho here. So I can cancel some terms. Here the density cancels, and the diameter here, and this expression for the Reynolds number can be written as 4 times the mass flow rate divided by pi d mu. This is often the expression of the Reynolds number that we use for internal flows, just because typically the average velocity is not what's specified. The mass flow rate is what will be specified. And so if the mass flow rate is specified, we just need the diameter and the dynamic viscosity for the fluid in order to solve for the Reynolds number, which again tells us whether the flow is laminar, fully turbulent, or if it's in between, we call it transitional. But now this diameter, or this definition of the Reynolds number, will be used for any internal flow, but not all flows have or through circular pipes. And we have non-circular pipes. For non-circular pipes, we define what is called the hydraulic diameter. so that the hydraulic diameter, D sub H, is just 4 times the cross-sectional area of the pipe divided by the perimeter. So if I have a square pipe or a rectangular pipe, then I would consider, well, what is the cross-sectional area, which we can calculate. That's the cross-sectional area for the flow divided by the perimeter of the flow, which is the length of the sides. And we would calculate the hydraulic diameter and use that expression in the Reynolds number, so that the Reynolds number just becomes 4 times m dot, which is the mass flow rate, divided by pi times the hydraulic diameter times mu. So if we have a non-circular pipe being used, you still use the same definition for the Reynolds number, but you just calculate the hydraulic diameter based on this expression of 4 times the cross-sectional area divided by the perimeter to get that expression. Now, when we're dealing with internal flows, whether it's laminar or turbulent is not the only consideration that has to be made. Recalling from fluid systems, we had the consideration of what are called entrance region length, and that's just the length of the pipe over which the velocity profile will be changing. And here I'm going to go to a figure here. So here, this is just for the hydrodynamic problem. We have a pipe length here, and we consider that here there's a rounded opening, a gradual changing of the diameter to the constant diameter of the pipe, so that we get this transition, so that at the very entrance of the pipe, we consider that the velocity distribution is uniform. But then due to the no-slip condition, the velocity goes to 0 along the inner radius of the pipe, and the velocity distribution starts to become non-uniform. And if there's a 0 velocity along the inside of the pipe with a maximum velocity along the center line, but in this inviscid core, where there's no rotation of the fluid occurring, although the fluid is still just moving left to right here, inside of this core, which is here, this blue line that is coming together, this is coming together all from around the inside of the pipe, and it grows together at the very end. At the very end, this blue line here is just the velocity boundary layer. The velocity boundary layer grows such that if I cut this along the center line, this representation would just be a thickness of that velocity boundary layer until it grows together at the center line. Notice that in this, well, here it's labeled as an irrotational core, which is there's no rotation of the fluid, which is due to the viscous effects not yet affecting this core on the inside of the pipe. So here we can see inside the inviscid core, right along here, this where it's flat, these are the places where the effects of the no-slip condition have not yet changed the velocity or change the velocity distribution. It's still uniform there. It's increasing in velocity, but it's still uniform until that boundary layer grows together. And then we have a single point here where the velocity is maximum along the center line and 0 still at the end. At each one of these places here, I'm going to just draw actually a green X. At each one of these places, though the velocity distribution is changing, the average velocity of the fluid is always the same. And that's because, again, the mass flow rate is the density times the cross-sectional area times the average velocity. If the density of the fluid is not changing along the length, if the diameter of the pipe isn't changing, the cross-sectional area is not changing. So if the mass flow rate, density, and cross-sectional areas are constant, the average velocity is a constant at any of these points along the length of the pipe. Now, this average velocity, because it's an average velocity at that position, it just says that the position or the velocities can change as a function of position from r equals 0 out to r equals capital R. So the shape of the velocity profile can change, but the average velocity stays a constant. So here, until this velocity boundary layer grows together, the velocity distribution changes, and in particular for hydrodynamic calculations, which is usually pressure drops that we're considering. Notice here that the slope here at the surface, this actually changes. This is velocity distribution. The velocity u, which is in the x direction, as a function of r, this gradient in the velocity distribution is what will be multiplied by the dynamic viscosity of the fluid in order to find the shear stress. This shear stress is changing along the length of the pipe in the hydrodynamic entry region because the velocity gradient is changing. But then once we get to the fully developed condition where the boundary layer grows together, this shape does not change anymore. This parabolic shape for the velocity distribution becomes a constant, and thus du dr becomes a constant. The velocity gradient evaluated at the inner radius becomes a constant, and so the shear stress becomes a constant. That just means that from the point at which we become hydrodynamically fully developed in the flow, now the pressure drop as a function of position becomes a constant. So for every foot, if the drop is, a tenth of a psi, then that's what it is. Or for every meter, if it's 1 kPa, then that's what it is, and it doesn't change. But along the length of the pipe in the hydrodynamic entry region, the pressure drop does change as a function of position. So dpdx at the beginning of this pipe is different from dpdx along the entire rest of the length of the entry region, but it becomes a constant once we get to the fully developed condition. So things that we have to consider for the flow is that, number one, is it a laminar or turbulent flow, which is just going to be based on the Reynolds number. And then we have to consider, is the hydrodynamic entry region a significant portion of the pipe? So let's say this hydrodynamic entry region was 1 meter in length. That means then if I have a pipe that is 1 meter long, then I have to consider that the effects of the hydrodynamic entry region cannot be ignored because the pipe length is exactly the same length as the hydrodynamic entry region. If the pipe is actually, the total pipe length is 2 meters, then that says that the hydrodynamic entry region takes up half of the total length of the pipe. And then for the other half, the velocity profile is a constant, and thus the pressure drop will be a constant. For the fully developed region, if I have a pipe that's 100 meters long, such that only 1 meter contains the hydrodynamic entry region, and then the other 99 meters is fully developed, then the effect of the hydrodynamic entry region on a pipe that's 100 meters long is going to be insignificant because for 99 meters of the pipe, we find that this is an expression that the hydrodynamic entry region is only that first meter, and 99 are in the fully developed. Typically, what we consider is that if the hydrodynamic entry region is less than 10% of the length of the total pipe, we can ignore what's happening in the hydrodynamic entry region and only consider what's happening in the fully developed region. Now, the significance again of that for a hydrodynamic problem is that the pressure drop as a function of x, dp dx, changes in the entry region. It's a constant in the fully developed region. Now, the consideration for that problem for heat transfer is through the definition of the thermal entry region length. In the thermal entry region, the temperature profile in the fluid is changing as a function of position. Now here, this blue line is an indication of the thermal boundary layer thickness. So this arrow is pointing to this blue bolded line here. Now, it grows together because, like in flow over a flat plate, if I have a plate, we have a thermal boundary layer and a velocity boundary layer, delta and delta sub t. They don't grow at exactly the same rates, but they do grow from the velocity boundary layer due to that no slip condition, in that the molecules right next to the surface have a zero velocity, and it's a fluid that is moving outside the boundary layer, so that for the velocity boundary layer delta, inside of that layer is where all of the velocities change and all of the velocity gradients exist inside that boundary layer. In the thermal boundary layer, outside the red line, the temperature is everywhere uniform, and the temperature of the molecules right next to the surface have the same temperature as the surface. So inside the thermal boundary layers where we have all the temperature gradients. Well, once we confine the fluid to flow through a pipe, whether it be a circular pipe or non-circular pipe, a velocity boundary layer and a thermal boundary layer grows from all of the surfaces that the fluid is in contact with, and it grows together at the center line of that pipe. Well, once the thermal boundary layer grows together, the shape of this temperature profile doesn't change anymore. Now, this is not exactly the same problem as the velocity boundary layer, or the hydrodynamic entry, or the hydrodynamic problem. This velocity profile does not change at all anymore, because if the mass flow rate is constant, the density, cross-sectional area times the average velocity, all of those would be constants in this problem. So the average velocity is a constant, and the shape of this profile is a constant. In the thermal boundary layer problem, the shape becomes a constant, but the magnitude of the average temperature does not become a constant. And that's because, let's say in this problem, where the black line is the inner surface of the pipe. Now, if I have a constant heat flux coming in from the surface of this pipe into the fluid, the temperature of the fluid is going to keep increasing as I apply a heat flux into the fluid. But once I get to the end of the thermal entry region, the shape of this profile will not change once we get to the thermally fully developed condition. And the reason that it doesn't change is, recall this expression of the temperature as a function of position. This shape gives me a dt dr. That shape that's the slope of that line. Well, I know that at this surface, where the fluid is in contact with the inside of that pipe, the heat transfer into the fluid can be written or the heat flux, let's say at the surface, is equal to minus k dt dr at r is equal to capital R, where R, that's the inner radius of the pipe. So this would be the conduction through the fluid would be equal to whatever this heat flux is. So if the thermal conductivity is evaluated at a constant value, then dTdr would be a constant, but the temperature of the fluid would keep increasing. So all that means is that the length of these lines These orange lines are indications of magnitude of the temperature. So here, well, actually in this particular problem, the way that this is drawn, the high temperatures along the center line. So it says that the heat transfer is actually from the fluid into the surface, because here is the temperature of the surface, and here's the temperature of the fluid. And if we're moving from left to right, this says, and according to the length of these lines, the highest temperatures along the center line, the lowest temperatures at the surface. So that says the heat transfer is occurring out. I'm trying to draw it as a flux. Is out of the fluid and into this surface. But that heat flux at the surface would be minus KD TDR. So as the temperature, as we move from R equals 0 to R equals capital R, the temperature is decreasing. So this heat transfer rate will be out of the fluid and into the surface. But this expression for a problem, if I had a constant heat flux out of the surface here, then all it says is that if the thermal conductivity is a constant and the heat flux is a constant, dTdr, the slope of this line would have to be a constant, which is a definition of the shape, but the magnitude could actually change. So when we're looking at expressions for the thermal interregion and the end of it, all this says is that for, let's say, in the thermal interregion, H varies. H is constant in, let's see, for thermally fully developed condition. And the reason we know that is because if I continue with the definition of this heat flux at the surface, this heat flux at the surface is minus KD TDR. This is a heat flux by conduction in the fluid, but this is also equal to H times the temperature difference between the surface and what is called the mean temperature of the fluid. T sub m is the mean fluid temperature. So just like there's an average velocity for the fluid at a particular position, because there is a velocity distribution. Again, here, this is a velocity distribution. The average velocity is just the average over the cross-sectional area through the pipe. But if there's a temperature distribution in the fluid, if we take the average value through the cross-section of the pipe for the fluid, we call that a mean temperature of the fluid. This expression, if the heat flux is a constant and the thermal conductivity is a constant, says that dTdr, the slope of this line, will be a constant. And if Ts minus Tm is the temperature difference between the surface and the fluid, H times that temperature difference is the heat flux. That would just be, the heat flux at the surface is equal to the heat flux by conduction into those stationary molecules right at R equals capital R. And it's also equal to the convection that gets the heat into the bulk of that fluid, which is the heat transfer coefficient times Ts minus Tm. Well, when we get to the thermally fully developed condition, H is a constant. In the thermal interregion length, which is from x equals 0 to whatever that length is, the heat transfer coefficient varies from an infinite value, like it does for flow over a flat plate, and then it becomes a constant when this temperature or this thermal boundary layer grows together, so that the temperature profile becomes a constant, or the shape of the temperature profile becomes a constant. This expression here for the heat transfer coefficient and also for the friction factor. The friction factor is what we typically look for out of just the hydrodynamic problem. The heat transfer coefficient is what we look for from the thermal problem. So if we consider here a pipe flow, So this could be circular pipe or a non-circular pipe. Here, the orange line is an indication of the thermal boundary layer that grows together, such that once it grows together, that is the beginning of the thermally fully developed condition. And here, this orange line is an expression of the heat transfer coefficient. It's infinite at x equals 0, and it decreases until we get to the beginning of the thermally fully developed condition, and then it becomes a constant. That's one of the characteristics of the thermally fully developed condition, is that the heat transfer coefficient becomes a constant. When we look here at the blue line, which is the velocity boundary layer growing together in the pipe, that is the beginning of the hydrodynamically fully developed condition, so that the friction coefficient, well, actually, this is the friction factor here, of F is infinite at x equals 0, and it becomes a constant once we get to the hydrodynamically fully developed condition where that velocity boundary layer grows together. So L sub T is what we call the thermal entry region length. And L sub H is the hydrodynamic entry region length. In the thermal entry region length, the heat transfer coefficient is varying. In the hydrodynamic entry region length, the friction factor is varying. So those two conditions, or those two considerations, have to be made when we are solving the thermal problem, because, well, when we're doing a duct flow analysis, in the thermal problem, we're particularly interested in the heat transfer that's occurring. But often when we're considering, well, if I have to pump a fluid through a pipe in order to provide some heat transfer either to the fluid or out of the fluid, the pumping requirements are going to be based on this friction factor, which are going to tell me the pressure drop that occurs along the length of the pipe. So that if I have a really short pipe where I consider that the friction factor is changing as a function of position, then I'd have to take that changing value into account when I'm calculating the overall pressure drop. If the entry region, or the hydrodynamic entry region is short compared to the total length of the pipe, and for the rest of the length of the pipe, the friction factors are constant, then if I'm looking at, well, what is the average value of the friction factor over the entire length, the longer I make the pipe, the closer the average will be to this constant value. The shorter the pipe, the closer the value will be to the average in the entry region length. The same applies for the heat transfer problem. The longer I make the pipe, such that the longer I have the heat transfer coefficient a constant, the closer the average value will be to this constant value. The shorter the pipe is, the closer that heat transfer coefficient will be to the average heat transfer coefficient that exists in the entry region. So we take not only into account, is it a laminar flow or a turbulent flow, but what is the length of that entry region, so I can determine whether or not I have to consider, is the heat transfer coefficient significant or is it not significant? So when I go back to this expression, if I rearrange it, it says that the heat transfer coefficient can be defined as the conduction heat flux minus K dt dr at R equals capital R divided by Ts minus Tm. So this becomes, and actually, and to make this specific, I'll make this H sub x, because dt dr, which is, this is a slope here, this changes along the length of the pipe inside the thermal entry region length. but then it becomes a constant because the shape of this profile becomes a constant once we get to the thermally fully developed condition. So the local values of the heat transfer coefficient are equal to minus K dTdr at R equals R divided by Ts minus Tm. So this this local value of the heat transfer coefficient, which is what's defined here, this line can be described according to this equation, which all this is the heat flux by conduction in the fluid is equal to the heat flux by convection in the fluid. So we can write these expressions for the heat transfer coefficient variation, so we can consider, well, how long, or we can consider how we should actually go about determining what is the average value of the heat transfer coefficient over the entire length of the plate. Or the entire length of the pipe, since we're working with internal flows now. Now, how do we determine, well, how long is L sub H, the hydrodynamic intra-region length? How long is L sub T, the thermal intra-region length? Well, those are based on expressions that are empirically developed. For a laminar flow, let's say for laminar flows, where the Reynolds number is less than 2300, L sub H, the hydrodynamic intra-region length, is approximated, because again, this is based on experimental expressions, but we'll write this is 0.05 times the Reynolds number times the diameter. So if we count again, the Reynolds number can be written as the average velocity times the diameter divided by the kinematic viscosity. Yes, times D. So this expression says that the higher the velocity, the longer the hydrodynamic intra-region will be. The more viscous the fluid, the shorter the hydrodynamic length will be. The greater the diameter, the greater the hydrodynamic intra-region length. So we can look and see, based on geometry, the fluid type, and the velocity of the fluid, how it affects the hydrodynamic intra-region length, such that if we increase the diameter or increase the velocity, the hydrodynamic intra-region length will be longer. If we increase the viscosity of the fluid, picking basically a thicker fluid, will decrease the hydrodynamic intra-region length. Now, this is particularly of interest for doing the hydrodynamic calculations, which usually centers around finding pressure drops, so that we can consider, well, how much pumping power needs to be supplied in order to move that fluid through the pipe. But the thermal intra-region length for a laminar flow is approximated here or calculated as just the hydrodynamic intra-region length times the Prandtl number. Or again, the Prandtl number is conceptually an expression of how well does the fluid diffuse momentum compared to how well does it diffuse thermal energy or heat. So this expression then is 0.05 times the Reynolds number times the diameter times the Prandtl number. Again, where I can write this is 0.05 times the average velocity times the diameter divided by the kinematic viscosity times the diameter times the Prandtl number. So here we can look and see that, the Prandtl number, if the Prandtl number is less than 1, it says that the thermal intra-region length will be shorter than the hydrodynamic intra-region length. If the Prandtl number is 1, the thermal intra-region length and the hydrodynamic intra-region length will be exactly the same. If the Prandtl number is greater than 1, the thermal intra-region length will be longer than the hydrodynamic intra-region length. So for a laminar flow, which is when the Reynolds number is less than 2300, we can use this expression to calculate, well, how long does it take for the shape of the temperature profile to become a constant, which is the thermally fully developed condition, or how long does it take for the velocity distribution to become a constant, which is the beginning of the hydrodynamically fully developed condition. So these two expressions are really important because they allow us to calculate a length, and we can compare that length to the length of the actual pipe and consider how well do I need to actually consider and calculate the contribution of the average friction factor to the constant value of the friction factor that would exist along the pipe? Or for the thermal problem, do I have to calculate this average value of the heat transfer coefficient compared to the constant value of the heat transfer coefficient that's going to exist once I get to the thermally fully developed condition? Now, when this is a turbulent flow, here, the Reynolds number again is greater than 10,000. Here we consider that the hydrodynamic intraregion length is approximately the same as the thermal intraregion length, which can be approximated as just 10 times the diameter. So if we have a Reynolds number that is greater than 10,000, indicating it's what we call fully turbulent, because of all of the mixing that occurs between the molecules that make up the fluid, when it's a turbulent flow condition, because the fluid doesn't just move left to right through the tube, it actually moves through different radii. I mean, and that the fluid is circulating a lot inside the pipe. Well, if the molecules are circulating, their ability to share momentum and to share thermal energy is very high. And so the length of pipe that is required for the velocity profile to become a constant and the shape of the temperature profile to become a constant is about the same, and it's taken to just be 10 times the diameter. So if the diameter of the pipe is 1 millimeter, or let's say 1 centimeter, then the hydrodynamic and thermal intraregion lengths would just be 10 centimeters, and that it would only take 10 centimeters of length of the pipe for the heat transfer coefficient to become a constant and for the friction factor to be a constant when it's a turbulent flow. So these designations of the length required for the heat transfer coefficient and the friction factor to become constant are things that we use when we're making calculations for an actual pipe. So is it laminar or turbulent? And is it fully developed hydrodynamically? And is it fully developed thermally? Now here's a plot from a figure from your text. I think it's a figure 8-9. And here, this is a variation. This is an expression of the Nusselt number as a function of x along the length of the pipe. This Nusselt number as a function of x is how you get the heat transfer coefficient as a function of x. And this is for two cases: when the surface temperature is constant and when the heat flux is constant along the pipe. Those are the two considerations that we'll consider for, or that we'll make for internal flows. And all that means is if I have a pipe with fluid flowing through it with a given mass flow rate, here's the second pipe, I can have a consideration here that I keep the surface temperature of the pipe a constant, or I can consider the problem where the heat flux on the surface is a constant. When the surface temperature is kept a constant, the heat flux will vary. When the heat flux is kept a constant, the surface temperature will vary. So that's all these. So the green line here is for the consideration when I keep the surface temperature a constant as fluid moves through it. The green lines are indications of how the Nusselt number changes a function of length along the pipe for a given Reynolds number. And here, each of these green lines is a different Reynolds number. And here, this is a non-dimensionalized expression of the length of the pipe, in that it's the length of the pipe divided by d, or the position along the length of the pipe divided by its diameter. So as we move along the length of the pipe, as if this Nusselt number is decreasing, once it becomes a constant here, the expression, this is where we consider, well, yeah, that's about right here, is where it becomes a constant value. Then the expression of the thermal entry region length is from x equals 0 to that point. And you here, as the Reynolds number increases, the place where the green line becomes flat gets closer to x equals 0 for the higher Reynolds numbers here for the heat transfer coefficient. Well, this is for the Nusselt number, which would give us a heat transfer coefficient. And again, the dashed lines are here for a heat flux being constant. So here it just indicates it takes a little longer when we consider x over d for the thermally fully developed condition to exist or to begin when we have a constant heat flux problem. So these expressions, these non-dimensional expressions here of the Nusselt number, again, where the Nusselt number is just h times d over k, so that the heat transfer coefficient is just k over d times the Nusselt number. So if we take these expressions for the local values of the Nusselt numbers for these two conditions, the local value of the heat transfer coefficient will be based on the local value of the Nusselt number. So when we find these expressions for Nusselt numbers, all they're doing is taking into account the flow conditions. Is it laminar? Is it turbulent? Is it fully developed, thermally fully developed, hydrodynamically? And we can use those expressions in order to write expressions for the heat transfer coefficients. The average, typically the average heat transfer coefficient is what we'd be looking for, because we want to consider, well, as fluid is moving through this pipe, how much heat is being added to it or removed from it as it moves through the length of the pipe. Now, with these expressions, these tell us, how we write. Well, it would direct us to the particular correlations that we need to find H, the heat transfer coefficient, whether it be a local one or an average one along the length of the pipe. But the way that we use those expressions is based on a general thermal analysis, which is a consideration of what's actually happening inside of the pipe. So, and we'll come back to this. Well, actually, I can do it right here. So we consider the thermal analysis part of the problem. If I have, actually, I do want to use a different page because I'll come back to this one to write some other stuff. When we consider the thermal analysis of the problem, all that is energy balances. If I have a pipe here with where I consider at the inlet and the exit of the pipe, I and E, there's a temperature at the inlet and there's a temperature at the exit of the pipe. So that if the temperature at the exit of the pipe is greater than the temperature at the inlet, it says that there was a heat transfer process that allowed for heat to go into the pipe from the surface here. Now, when this fluid flows through the pipe, it comes in with a given mass flow rate and a specific heat, and a mass flow rate and a specific heat at the exit here. So M sub I, C sub P. All right, there we go. So if there's energy that comes in and energy goes out, the increase in the energy of the fluid from the inlet to the outlet is the is the amount of energy that came in through the surface of the pipe. So if I draw a control volume around all the fluid that's moving into the pipe, again, the fluid comes in with some enthalpy, leaves with some enthalpy, such that any difference between the two would be whatever came into or went out. If the exit temperature is lower than the inlet temperature, that means a heat transfer was out of the fluid. And here we're talking about the surface, because if I draw the control volume around all the fluid inside the pipe, the fluid is in contact with the pipe on the inner surface, at the inner surface of the pipe. So here, if I just do an energy balance on the fluid, if I consider that the rate of energy in must be equal to the rate of energy out for steady state conditions, well, the rate that energy comes in is with the fluid, m dot n times the specific heat as it comes in, times the temperature at the inlet. This gives me a heat transfer rate, and this is kilograms per second times kilojoules per kilogram Kelvin times the temperature in Kelvin, or here being Kelvin. And that tells me the temperature, or the amount of energy, is be some kilojoules per second, plus the heat transfer rate into the fluid from the surface must be equal to the mass flow rate at the exit times the specific heat at the exit times the temperature at the exit. Now here, for steady conditions, and a constant specific heat, this expression can be written as Q dot is equal to Q. Now, if it's a steady condition, the mass flow rate at the inlet and the mass flow rate at the exit are the same. They can just be written as a mass flow rate, M dot. If it's a constant specific heat, the specific heat at the exit and the specific heat at the inlet are the same. So I can write this as M dot times C sub P, to be the temperature at the exit minus the temperature at the inlet. So if there's no heat in, then the temperature at the exit and the temperature at the inlet would be exactly the same. If there's heat in, the temperature at the exit is greater than the temperature at the inlet. If the heat transfers out, making this a negative, it says then that the temperature at the exit will be less than the temperature at the inlet. This is just based on conservation of energy applied to the control volume here for open system analysis. That's just from thermodynamics. But now when we delve into it a little deeper, well, this heat transfer rate in is by a convection process, in that the fluid is in contact with the inner surface of the pipe. So the surface flux from the pipe the surface flux from the pipe here is by convection, and it says the heat flux from the surface, Q dot sub S, is equal to the heat transfer coefficient times Ts minus Tm. Now that heat flux, defined as a heat transfer coefficient times Ts minus Tm, well, recall that for in the figure for expression of H as a function of X, the heat transfer coefficient varies as a function of X. So I'm going to put a subscript here on X, because if we're in the thermal intra-region length, H varies from an infinite value at the inlet, and it decreases until we get to the thermally fluid developed condition, where H then becomes a constant. But here, this expression for this heat flux describes how heat gets into the fluid by convection. And this expression is just for the overall energy that's transferred into the fluid, such that it's going to affect the temperature of the fluid. If I don't have a heat flux by convection, then this heat transfer rate becomes zero because Q dot would just be equal to the average heat flux from the surface times the inside surface area of the pipe. So this is Q, I'm writing this, Q dot sub S average times the surface area. So then that would be the average heat flux times here, this would be Ts minus Tm, and this would have to be an average value of the temperature difference because this temperature difference between the surface and the fluid will change along the pipe, length of the pipe, times the surface area. So this expression of a heat transfer rate for a surface heat flux from the pipe, it would be equated to the enthalpy change that occurs in the fluid, and that's just the sum of the internal energy plus the flow energy associated with the fluid. But when we're considering an expression for, or expressions for the thermal analysis of these problems, it's going to be based on, there's a heat transfer rate into the fluid if we're heating the fluid from the surface from the surface of the pipe into the fluid, so that the energy in the fluid is increasing if we're heating it. But we can heat it by using a constant surface temperature, or we can do it by providing a constant surface heat flux. So those two methods for providing heating, or let's say providing heat, that'd be Ts is equal to a constant, or the heat flux is equal to a constant. Those are the two problems that we would consider. Now, the first one we'll consider is the constant heat flux problem, because that one is very easy to conceptualize. And so I'll go back to this figure. So here, imagine a pipe with an inlet and an exit, and we apply a heat flux. Now, this applied heat flux can be by, let's say, an electric resistance blanket or by a constant radiation flux, but by some means, we're providing a constant heat flux on the outside of this pipe, so that applied heat flux on the outside of the pipe would then be, that heat would be conducted from the outer radius to the inner radius of the pipe, and it'll supply a constant heat flux to the inside of that, the inside surface of the pipe, so that flux would then be into the fluid, and that flux would be by convection into the fluid here. Now, this plot is a plot of the temperature as a function of X along the length of this pipe. This lower orange line is a temperature variation of the fluid. This upper line is a temperature variation of the surface. So here, T sub M, again, where T sub M is the mean temperature of the fluid, T sub S is the surface temperature of the pipe. Now, recall that I wrote an expression that said by the energy balance, the heat transfer rate, which would be just this applied constant heat flux times the surface area of the pipe, is equal to the mass flow rate times the specific heat times the temperature at the exit minus the temperature at the inlet. If I redefine this expression for the exit temperature, the exit temperature will just be the applied heat flux times the surface area divided by the mass flow rate times the specific heat plus the inlet temperature. Well, this surface area for the pipe can be defined as pi dl. So if I write this as the heat flux times pi dl divided by m dot c sub p plus the inlet temperature. So this says that the temperature at the exit, where the exit is at X equals L, is just the heat flux times pi dL times m dot C sub P plus Ti. Now, this heat flux, if it's defined on the outside of the pipe, the surface area would be the outside surface area, which would be pi times the outer diameter of the pipe times the length of the pipe. If the heat flux is defined on the inside of the pipe, then the heat transfer rate, capital Q dot, is just the heat flux times pi times the inner diameter times the length of the pipe. So the position for the definition of the heat flux is critical in these problems, in that if the heat flux is defined on the outside, the surface area where that heat flux is being supplied must be multiplied by the surface area over which it's applied. So if the heat flux is on the outside, the air is the outside. If the heat flux is on the inside, then we have to define the area on the inside of the pipe. But this expression just says that the outlet temperature, the exit temperature, is a function of the applied heat flux, the surface area, the mass flow rate, and specific heat. Such that if I increase the mass flow rate or the specific heat, the temperature increase from the inlet to the outlet is decreased as I increase the mass flow rate or specific heat. If I increase the flux, the diameter, or the length, keeping everything else the same, I'll increase the temperature difference between the inlet and the exit. Now, this is the temperature at the exit, and this is the temperature at the inlet here. Well, I can make this expression just a function of X because this is the temperature at the exit, where the exit is at X equals L. The temperature at any position in X would just be the heat flux times pi d times X divided by m dot C sub P plus the inlet temperature. So I could actually find the temperature anywhere along the length, and notice that this is just an expression of a linear temperature variation. This is Q dot sub S times pi times d divided by m dot C sub P. All of those are constants. So that's a constant times X plus Ti. So that constant multiplied by X is just the slope, and Ti is just the intercept here. So when X is equal to 0, the temperature at X equals 0 would just be Ti. But the temperature will be increasing such that the temperature at X equals L would just be the heat flux times pi d times L over m dot C sub P plus Ti, which is the previous equation. So this just describes this line here. Now, the expression of the surface temperature as a function of X has this different shape associated with it. It's only linear in the fully developed region. And the reason that it's only linear in the fully developed region is because in the fully developed region, H is a constant. The heat transfer coefficient does not change. Remember, in the entrance region, if I do an overlay here, let's try this. H as a function of X. So here is L, and if I bring this line down, this expression here would be L sub T. This is the thermal intra-region length. The heat transfer coefficient varies from infinite, and then it becomes a constant here. Now, we said that the heat flux on the surface is the heat flux by convection, which would be H times Ts minus Tm, where Tm is the mean temperature of the fluid. Now, here in this problem, the heat flux is a constant. So if I rearrange this expression to solve for the surface temperature, it says that the surface temperature would be that applied heat flux divided by the heat transfer coefficient plus the mean temperature of the fluid. Now, so Ts is the upper orange line here. We have the equation for the temperature of the fluid, the mean temperature of the fluid, and actually let me write this, add here, this is Tm. That's the mean temperature of the fluid. If I substitute this expression into this one for the surface temperature, here, if I write this as Ts is now the heat flux divided by H plus the mean temperature of the fluid, which is this expression of the applied heat flux times pi dx over m dot C sub P plus Ti. So this is how we define the expression of that surface temperature. Now notice here, when the heat transfer, if this heat transfer coefficient being an infinite value at x equals 0, this term goes to a 0. And so it says then that if at x equals 0, Ts, this is a function of x by this equation. So I'm going to, it's not, this first expression does not immediately indicate that it's a function of x unless you're considering exactly what Tm is defined as. But now that I substituted in the definition for Tm, here, Ts is a function of x. So I'm just going to add here that it's a function of x. So if I evaluate this expression at x equals 0, this becomes the heat flux divided by an infinite value plus a 0 plus Ti. Well, any constant divided by infinity approaches a 0. So this says that the surface temperature at x equals 0 will be equal to Ti. So here, this expression at x equals 0, there's a temperature difference. It's lower than the temperature difference at H. Here, they're just not considering it to be an infinite value, some calculatable value here, which is, if we don't consider H infinite right here, then this would be some magnitude added to Ti, which is what this is here. This is whatever the temperature is at Ts at x equals 0, and here's a temperature that is Ti. But now, what happens? So here, H decreases as a function of x. Well, as H decreases, here I'm looking at this equation here. If H becomes lower, it's not an infinite value, then I get a non-zero positive value for this first term that is added to the expression of Tm, which is a function of x. So the second and third terms here that define Tm give us the equation for this lower orange line, and this expression for the upper orange line, Ts, is calculated based on how this value changes. So the surface temperature is going to increase because Tm is increasing, plus this expression of the heat flux divided by the heat transfer coefficient. And the heat transfer coefficient is decreasing as we move through the entry region. So the further we move in x, the higher this temperature is, but the lower this value becomes, the higher this value becomes because H is actually decreasing. So the effect is that this temperature difference, this is the temperature difference between the surface and the fluid. This temperature difference gets larger as we move through the entrance region because the heat transfer coefficient is getting smaller while that heat flux is a constant. So this term gets larger. It's added to the increasing value of the mean temperature of the fluid, which is the second and third terms here, so that this temperature difference grows until we get to the beginning of the entrance region, because at that point, H becomes a constant. The heat flux is also a constant. So this first term becomes a constant once we get to the fully developed condition, but the surface temperature is still going to increase, and this is going to increase linearly in that I'll have an a slope times x plus two terms that are now the intercept, which is just Ti plus the heat flux divided by H, because the heat flux is a constant. H now becomes a constant. added to the constant value that is the inlet temperature of the fluid. So this is why here, once we get to the fully developed condition, these two lines move parallel to one another, and this delta T just becomes a constant value. And that constant value, that is the temperature difference, is just this heat flux divided by H, because both of them will be moving with this with the same coefficient or slope multiplied by X. So when we're considering an expression for the temperature variation in the fluid, when we have a constant heat flux, the temperature of the fluid, T sub m, is going to change linearly for a constant heat flux because we're just constantly dumping heat into the fluid, changing its temperature. The surface temperature varies nonlinearly in the entrance region because the heat transfer coefficient varies nonlinearly in the entry region. But once we get to the thermally fully developed condition where the heat transfer coefficient becomes a constant, now the surface temperature will increase linearly according to this expression, where H is what causes this variation in the temperature on the surface to look like it does in the entry region here. So the expressions of heat transfer for a constant heat flux problem are relatively straightforward in that the temperature variation of the fluid through that pipe is going to vary linearly from the inlet to the outlet because we're just adding heat to the fluid. The temperature variation of the surface as a function of X becomes linear once we get to the fully developed condition. It's nonlinear in the entrance region here. So when we're calculating either surface temperatures or fluid temperatures, this is how we would do it for a constant heat flux problem. Now, when we consider the constant surface temperature problem, that one's a little bit different because now the flux is not externally forced onto the fluid. Again, the way we would carry this out is to maybe wrap this in an electric resistance heater, such that when we plug it in, we know the heat transfer rate divided by this surface area, and that gives us what the heat flux would be into the fluid, or at least into the pipe, and then the heat flux into the fluid would be divided by this surface area that's on the inside of the pipe. But for the constant surface temperature problem, here the surface temperature is kept a constant rather than the flux being kept constant. This would be carried out by, let's say, if I have, in this case, if I'm heating, that says then that the fluid temperature is increasing as we move along the length of the pipe, but now it has a limit. The highest temperature that the fluid could ever become would be what the surface temperature is on the inside of that pipe. That's the highest it could ever become. Well, the temperature difference between the surface and the fluid is what drives the heat transfer, because again, the heat flux on the surface is H times Ts minus Tm. Here, Ts is held a constant. The heat flux is not. So the heat transfer coefficient varies. The mean temperature will vary, so the heat flux will actually vary because H is varying and the mean temperature is varying. So if the heat flux is defined by Ts minus Tm, if I make the pipe long enough and the fluid temperature becomes the same as the surface temperature, then at that point I have no more heat flux that's occurring. This expression of the temperature variation of the fluid as a function of X, so that there's an asymptotical approach to the temperature that is Ts, we can describe this by a decaying exponential along the length of the pipe. And so this is where we'll pick up the next time and just look at, how do you solve a couple of these problems and for the conditions of a constant heat flux or a constant surface temperature. But here again, just consideration of, well, what is the value of the heat transfer coefficient is what's important for these calculations, because that's what defines the heat transfer rate by convection or the heat flux by convection, such that the heat transfer rate, again, is just the heat flux times the surface area over which that convection is occurring. All right, well, that's it for today, and I will see you again on Wednesday. The exam particulars are posted just like they were for exam number 1 in that module, the exam module. We'll go through lecture for the first 30 minutes, and then you'll have your exams that will open up for you to start on the 5 minutes later. So that's it for today. I have office hours again, 2:30 to 3:30 tomorrow. So if you have questions, definitely come by. Otherwise, if you've been working through the problem assignments, you should be very well prepared for the exam. All right, that's it. Hope you have a good rest of the day, and I will see you again tomorrow or on tomorrow during office hours or on Wednesday. Have a good day. See you.